This is question 5 of the 2019 Scholarship Physics exam. What do we got? Crumple zones are part of a vehicle that are designed to deform during collisions, converting kinetic energy into heat and deformation. As a test, 2.2 kg model truck moving at 8.3 meters per second collides with the back of a stationary model car that is fitted with the crumple zone. Immediately after the collision, the model car is moving at 5.5 meters per second. If the model truck is not damaged from and a constant force of 500 newtons is exerted during the collision, calculate the maximum change in length of the model car as a result of the collision. Well, explainable working. Right, so this is just going to be straight off the bat. I can see it's going to be a momentum question of some sort. I don't know what the velocity of the truck is afterwards, so I'll probably find that out now. I'm not sure whether I need to fuse an energy consideration with the momentum consideration. Often questions you got to add in that you got to write out the energy formula, or you write out the momentum relationship, and then you you'll substitute that into the energy formula. But I dare say I can actually, looking at it, 1, 2, 3, 4. I can definitely find the velocity of the truck. Can I? Yes, I probably can. Of the final velocity of the truck. So I'll write out, you always start with momentum initial is going to be equal to momentum final. There's no external forces that I can see because we're just ignoring friction. I'm going to do everything algebraically because that's how I like to roll. So we've got mass of truck, velocity of truck is the only momentum to begin with. And we've got that we've got that mass, it's there, we've got that, and I'll chuck in above it. So model truck, this is MT, and this is VT. Pays to write it as you go. This is going to be equal to, we're going to have mass of car, velocity of car. So this is going to be the mass of car, and this is going to be the velocity of the car, VC, plus, because it's a momentum exchange, so this is going to lose some momentum to that, and it'll have a little bit of momentum left over. Mass of truck, and this is going to be final. Oh, no, it doesn't even matter actually. It's just mass of truck because it doesn't change. And this is going to be velocity of truck final because that's the only thing that's going to change. And I've got that because it's just over here. The only thing I don't have is the velocity of the truck final. I might as well find that out because why not? And I'm probably going to need that because there's going to be energy to crush the car. Work is going to be needed to be done to crush the car. Probably there would have been some loss in energy because no collision is fully elastic unless you've got some mechanical impedance going on. So there'll be some sort of energy loss that'll go into heat and probably crushing of the truck. So let's do that. We'll just rearrange, we'll find velocity of the truck final. So we're going to go rearrange everything for VTF. So MT VT minus mass of car, velocity of car, divided by mass of the truck again, and that'll equal to the velocity of the truck final. And I'll just do that on my calculator quickly. So you can see I plugged that into my calculator and I've got 4.54 is equal to 4.54 meters per second -1. Just do the sniff test. Yeah, it's going slower, so I didn't screw anything major up. If that was bigger, I'd be running into problems, and if that was like 1, then I'll get a bit iffy about it. So now we're going to have find loss in energy, find change in, or it's just E, change in energy lost. I can just leave it out. That's energy. If I put a hat on top, it's a vector, and that'll be an electric field because energy is a scalar. So find energy lost. That is going to be energy kinetic initial minus energy kinetic final is equal to, we'll call this, half mass of truck, velocity of truck squared, because that's the initial energy, minus, and then we've got the mass of truck, velocity of truck final squared, plus mass of car. Oh, I need halves in there as well. Half, and I've got the half as well, so it's half, velocity of car squared bracket, and this is equal to E lost. And I'll just do this on my calculator quickly. And hopefully you can see all my working in there. You can pause the screen if you want to. We get 30.55 joules. So 30.55 joules. So this is the energy lost to the environment. We're going to make a massive assumption here, which is kind of true, and I'll get into why-ish soon. We'll just say energy is equal to work done. Work done on the crushing of the car, or work done on the car, which is work is equal to force times distance, because they gave us a force. I mean, that's the only way you could possibly do it. I suppose you could probably, no, that's the only way you can do it I can think of. So in other words, distance is going to be equal to work over force, and that's just going to be equal to, was it 30.49 divided by 500, and if I do that quickly, that's 0.061 meters. There we go. So that's, what is that, 6.1 centimeters? Sounds about right. Right, state the major assumption you had to make in order to complete the above, and give reasons why the assumption is unlikely to be correct. The major assumption was that all the energy went into deformation. Typically, some goes into sound and heat. There's a Veritasium video where they use a gun and fire it like here's a block of wood. This is upward. So the block of wood is just resting. They fire the bullet into the block, and then it launches off because it's an inelastic collision. The bullet lodges into the block. And both times, so they fire it straight into the middle of it, and then they fire it off to the side. And the crux of the video was, why do when you fire into the middle and off to the side, the blocks go to the same height? Because when you fire off to the side, it's rotating. But when you fire in the middle, it's not. And then when you do the energy consideration, you think, well, that doesn't make any sense. If you fired it off to the side, it must have more energy, because it's still got, both of them have gravitational potential. They both get up to the same height. But the one that's rotating has rotational energy, so that doesn't make any sense at all. But what you forget about is that 90% of the energy goes into lodging the bullet into the block. So typically, in most collision-y things, I'd say about 90% of energy is lost to deformation. Probably maybe 10% would be change in speed, and only a very small portion is actually lost to heat. So I'll pause and just write a nice answer. But yeah, that's why. Right, so I also checked in, I said, had to assume conservation of momentum, no external forces, also that 100% of energy went to deformation, when really some energy would have gone into sound and heat. Right. Calculate the time the two vehicles are in contact. There's been some exchange of momentum. We know what the change of momentum was because we can just look at one of them. Probably just look at the car because it went from 0 to that speed. So we know what the change of momentum is. We know what the force is because they gave it to us right there. So we can just use change in momentum is equal to force times time, or FT, there you go. And we know the change of momentum is just the mass of the car times change in velocity of the car, because the change in momentum one is equal to the change in momentum the other. Momentum is kind of like money, except for without all the depreciation stuff going on. It's literally just, it's like money. Well, it's not like money. If one loses a certain amount of momentum, the other gains that exact same amount. You can't really destroy it unless there are external forces going on. I'll make that a bit of V. And that's meant to be a delta. So this is going to be equal to, what is that going to be equal to? I'll just calculate quickly. I'll quickly calculate that. It's 8.32. So it's 8.325 kg meters per second -1. So that's a change in momentum. Rearranging, change in momentum over force equals time, which equals, I'll just divide this by 500 because I'm lazy. And we get 0.01665 seconds, and I'll just chuck down here, t equals 0.017 seconds. That'll do. They're never that picky on units. Right, I'll shift this calculator out of the way. Next question. Using physical principles, explain why it is a cause for concern if vehicles do not have crumple zones. This is like a level 2 internal. I might just pause it and then write out a full answer and then just explain it a bit easier. Right, so I just said a crumple zone is designed to reduce the acceleration / force. I'll put acceleration / force because you literally just divide by the mass of you. Acceleration divided by mass gives you force. So you can just use them interchangeably. That a passenger experiences. It does this by increasing the time of duration of a collision. A lot of times I see kids that says it increases the time of collision. I suppose that's actually kind of right. You can word it such that it sounds a bit bizarre. Assuming the car in all situations comes to a complete stop, this means this means change in momentum will always be the same as change in momentum. Always be the same. Maybe I should put a full stop there. I definitely should not be an English teacher. As change in momentum equals force times time. If we increase the time of collision, we decrease the force on the passenger and reduce the chance of injury. This is like a level 2 internal that my students do. And what I'm looking for in a question like this here is the fact that change of momentum, for pretty much, if you assume change of momentum is the same, if you assume the car is going to stop, then this will be constant. Because you're going to have to go from whatever momentum you did have to none. Or just assume the same situation. So this is the assumption that you need to make. Then you need to say that if that is the same, if we increase the time of collision, so you use a crumple zone to increase the time of collision, then the force acting on the passenger will reduce, obviously, which will reduce the chance of injury. What other things you can do? You can also say that crumple zones help dissipate energy. Maybe I should have written that in here as well, but I can't be bothered. But I'll just talk about it. So crumple zones, they dissipate energy because the work is done on the car and not the person. So if you did the work on the person, you'd end up crushing the person, whereas if you did the work on the car, you crush the car. But I mean, cars are replaceable. People are not at the moment. Waiting for that Elysium movie to be real life where they heal them with those fancy machines. Anyway, using physical principles, explain how a seatbelt can reduce the risk of injury in a collision. I have no idea what they're going on with this question, but probably, how do they talk about it? So you probably want to be with the car so you don't launch yourself at the windscreen. So you want to be with the car when you do the collision. Probably also you can say the fact that if you didn't have a seatbelt, you'd probably smash your head on the steering wheel. Head, small surface area, steering wheel, small surface area. So your force would be put over a smaller area, which means your pressure on your skull or head or whatever would be ginormous, which would damage your brain. So that's probably another example. So I'll just pause and write out a semi-coherent answer. Right, so I've said the seatbelt keeps the passenger attached to the car. It's kind of the point. So if the car decelerates, I don't think that's a word, but negatively accelerates, who knows? Decelerates slowly. I haven't spelled it right either. The passenger experiences that acceleration, that negative acceleration, and doesn't get launched into the windscreen. Don't know how to spell launched either. That's Newton's first law in action. So you just continue on with the same velocity that you had under your own inertia. The seatbelt also has a larger area, so given the same force / acceleration, the acceleration, if you just divide by mass, you get force, the pressure acting on the passenger will be reduced because pressure equals force over area. This is year 11 physics. Woohoo, going back in time. If all the force acted on your skull, so this is a counterexample, when you hit your head on the steering wheel, because you didn't wear a seatbelt, the pressure could be so large that the damage would occur. That is not very good English at all. This is a tricky question because they're not really, it's like year 11 physics, kind of. But yeah, I hope that sort of answered it. Maybe I should have talked about momentum as well. So when you do these sort of questions, these real vague questions, try and talk about anything. If I was going to keep on going, I'll probably say use a change of momentum thing. So because your seatbelt has attached you to the car, when the car decelerates slowly because you've got a crumple zone, that means you'll be decelerating slowly, so your time of collision will be less, the total force on you will be less, the total pressure will be less, and it is the pressure that causes the damage, not so much the force. The force then acts on you, which causes pressure, that causes punctures and stuff like that there. But that's another thing to think about. That's why you have airbag, increases the area, which also it crumbles a little bit. So there's that in it as well. But it also increases the area a lot, so it covers your body. Maybe I should have talked about that as well. But they're all things to think about.